It's really a pleasure to introduce Professor Jonathan Weare from the Carr Institute of Mathematical Sciences at NYU. John got his PhD in applied mathematics at Berkeley, and then was a Carr instructor at NYU, and then spent many years on the faculty in the departments of mathematics and statistics at the University of Chicago, and then moved back to New York, so closer to here. So I was able to take the train up one of the first excursions since the start of COVID. John's done a whole lot of super interesting work in Monte Carlo methods, numerical linear algebra, particularly randomized numerical linear algebra, with applications to geosciences, computational chemistry, so on and so forth, and has won a host of prestigious prizes along the way, the Dewey Early Career Prize, the IMA Prize for Mathematics and its applications, and a host of other things. So really pleased that John could spend the day with us today and talk about Weare events.
Thank you very much for the invitation. It's fun to talk to you guys. I guess I'll talk to you more later. Let me mention my collaborators here. So this has been really, I'm going to talk to you about a part of a really pretty long-term effort by really that started with Dorian and I to, so Weare event ideas and Weare event algorithms are pretty common in molecular dynamics, in chemistry. But the approaches to studying Weare events in earth sciences, it's a little bit more traditional. So running models for a long time until you see the event. So our goal, starting early so Dorian's in Chicago, and he moved there about the same time I did. And so our approach starting early in our relationship, or our idea starting early in our relationship, was to try to push some of these Weare event methods into earth sciences. And we focus mostly on atmospheric science. Then we had some great students who really did the work and made things come out well. So one of them is Rob Weber, and he graduated last year. He worked on many things, among them this project on hurricanes, and I'm going to show you the first part of the talk. So Samuel Hayden is a postdoc now at Toronto. He really was essential for the planetary science application that I'll show you in the second part of the talk. Okay, that's his expertise. I'm not actually going to talk about the work with Justin and Ed. Ed is one of my colleagues at Courant. He's a specialist in atmospheric dynamics, and Justin is a PhD student also graduating this year who worked on applying Weare event ideas, not Weare event sampling. It's more of a Weare event analysis idea for sun-south stratospheric warmings. But it's all in this same kind of larger effort that we've been pushing along. Okay, so that's everybody. Okay, so if you're talking to Yusuf a lot, then I probably don't need to convince you that Weare events are interesting and worth studying. So some examples, and I chose these examples because they've intersected the group's research, but there are more. So I'm going to talk to you about hurricanes in a moment. The idea so then there's major blackouts or conformational changes in large cloud molecules. The connecting tissue here is that the models that one would use to study such an event require a very short simulation timescale. Okay, but the event happens over a much longer timescale. So for example here, my model of this, this is an insulin dimer, dissociation of insulin dimer. My computational model of this, my molecular dynamics simulation, which would include a zillion waters around it, needs about a femtosecond timescale, 10 to the minus 15 second timescale. But I actually don't remember exactly the timescale of this dissociation, but imagine it happening on, say, 10 to the minus 3 or something. So much, much slower. Many, many orders of magnitude across. And something similar happens with, although not as extreme, happens with the most intense hurricanes, which is that they might happen once every 10 years, or even less if you're really focused on a particular region. And your timescale for simulation might be really do a high resolution, so it might be minutes. Okay, so that's the kind of problems that we're interested in, at least with this talk. And you have a few options. So one is to build a really, really fast computer. And I think when most people think of that, they think of piecing together a bunch of IBM chips in some giant cluster on a bunch of nodes. But actually, you can go even farther. If you're really focused on a particular application, you can actually design the hardware to be special purpose for that application. And that's the case with molecular dynamics with this Anton computer, which is done by which was put together by D. Shaw specifically for molecular dynamics. Okay, another approach would be to say, well, I just can't afford to simulate this high resolution model. I'm going to try and build a model that is cheaper, so lower resolution, maybe fewer variables, but it could be less complex in other ways, so that I can take, for example, bigger simulation time steps. But the hope would be that you could do that in a way that preserves accuracy, at least in the phenomenon that you're interested in. Okay, so you might completely not resolve some phenomenon, but as long as those are phenomena you don't care about, you might be okay with that. Okay, that's not surprising, but that's a hard thing to do. For this talk, we're going to discuss rare event simulation. And the idea there is to, given a model whose fidelity you're happy with, a sufficiently accurate model, but one that is too expensive to just simulate forever and generate many realizations of the rare event, instead I'm going to try and trick the model the way I use it. I'm going to try and trick it into undergoing the event that I'm interested in more frequently. And the key is that the way that I trick it, I want to make sure I can still compute the statistics as if I never tricked it. Okay, so I don't want statistics for some other model where the rare event happens more often. That's useless. I want statistics for the real model that I trust. But to get that accurately, I need to somehow convince the model to show me the rare event. Okay, so this talk is all down here. Okay, and there's different ways to do rare event simulation. To do that tricking, we're going to use something called trajectory splitting, which is well suited to big problems where you might be working with a legacy code for the model. Okay, you didn't write the model code, so you just have the ability to press go and stop. Okay, so what do I mean by a rare event? Well, let's take this definition. So just xt is all the degrees of freedom in the model. So if it's the weather, it's all the variables at all the grid points. So it could be a billion variables or something. And the event, let's call A. So this would be something like, I look at the patch of Earth that I'm evolving the weather on, and I see, yes, there's a really intense hurricane in that patch of Earth. Okay? And that's, if I look at any fixed window of time in any fixed place on Earth, that's a low probability. Okay? This could also depend on the initial conditions. So if I start from, I'm not explicitly writing that it depends on the initial condition, but if x0 corresponds to no hurricane at all, and t is a relatively short time, then you have a very low probability of a hurricane being there after time t. Okay, but you might be interested in other things too, like maybe the most likely from my forecast, the most likely storm path is here, but for whatever reasons, I'd really like it to hit over here. I don't know how many of you remember this particular picture. We won't go into the reasons, but that's a rare event. In fact, it didn't happen. Okay, so this slide is going to try and walk you through the high-level idea of how these splitting schemes work. So, in the most basic estimator of this probability, let's call it DNS, direct numerical simulation, I would generate n simulations. They don't communicate at all. I just do it. I can do it in serial or I can do it in parallel. However I decide to do it, I'm going to simulate the model n times. And then I can ask, of those n times, how many times did the event occur? Okay? And then just take that frequency as my estimate of the probability. So that would be the case where these w's, these weights, were all 1 over n. Okay? The simple, standard, basic estimator. All these weights would be 1 over n. And I'm just counting the number of times I ended up observing the rare event in these model simulations. What diffusion Monte Carlo is going to do, and I call it diffusion Monte Carlo, you could call it sequential Monte Carlo, or splitting. Any of those names are fine. Probably other names. What it's going to do is it's going to introduce some interaction between those simultaneously evolving simulations. So they're no longer going to be done without any communication. Every once in a while, they're going to stop, share some information, and then continue the evolution up to time t. Okay? As a consequence, I am going to have to introduce weights that are not all going to be 1 over n. Okay? But it is still going to be true that the expectation of the left-hand side is still going to be the right-hand side. Okay, so this is an unbiased estimator. It's not the most basic estimator, but it's an unbiased estimator. And it'll be true that as n goes to infinity, this converges to the probability on the right. Okay, so those basic properties of the most basic estimator are preserved. What I want to do is make sure that this random variable has lower variance than the original estimator. That's the whole goal. Okay, so how does it do it? Well, imagine these are my parallel simulations. Okay, you see in the background this blue function. I'm going to say what that is in a second. The horizontal direction here is that, let's imagine it's just a one-dimensional state space. So these particles are just evolving. The model just evolves in that one-dimensional state space. So DMC is going to work in 3 steps. The way I'm going to describe it. The first step is that they just do their thing. You evolve the weather for a day from each of these each of these is a different state of the weather. Okay? In the first step, you just evolve each of them independently for a day. Okay. In the second step, I look at this blue function in the background, this blue curve in the background, and I use it to assign a weight or a score to each of my samples. So you'll notice that each dot is in the same position on the x-axis. That hasn't changed going from the second line to the third line. What's changed is the size of the dots. I'm using the size of the dots to indicate the value of this score. So where the weight is, where the background function here is high, the weights are larger. Where the background function is small, the weights are smaller. Okay? So I haven't really done anything yet. Where the interaction really happens is in this last step. I am going to preferentially remove or delete from my family of states that have small weight, small dots, and preferentially duplicate states that have large weights. So in this way, if you compare this ensemble or this ensemble to this ensemble, you can see what I've done. Well, let's compare the second to the fourth. You can see that what I've done is I've refocused the samples around the center where the weight is high. Now I'm going to come back to the top and repeat. So that means this is the expensive step. This is the expensive step. Everything else is basically free. So these samples that have no weight, in the next time around, I'm not simulating them. I'm not expending any effort on them anymore. They're gone. But I'm spending way more effort on what's going on around the center region. Okay? Now, it is important that there needs to be some stochasticity in the model. There's different ways to insert that, and actually the two projects that I'm going to show you do it in very different ways. But I need to make sure that in this next go through the process, that these aren't just going to stay on top of each other. Okay? There's no point in doing the same simulation 3 times. So there needs to be some stochasticity that's going to drive these apart so that they spread like this again. Okay? So that's one pass through the algorithm. And you can sort of see intuitively that I am focusing my computational effort near this center, near this blue curve, where this blue curve is high. When I do this, I need to adjust my weights. You could imagine, for example, that maybe if these weights were all 1/n at this stage, maybe each of these guys now has a weight of like 1/3. That's sorry, 1/3, 1/3 whatever the weight was before, because they got copied 3 times. So there's different ways to assign the weights so that this left-hand side remains an unbiased estimator of the right-hand side. But you can imagine that's sort of what's going on. These really shouldn't be here under the original dynamics, and so they should have smaller weight. Okay? So the idea would be that this is I put this blue curve here to focus simulation on the rare event region. So this is like like a tail probability for the original dynamics. It doesn't want to be here, but I keep gathering my particles and putting it there. Okay. All right. So let me talk about that blue function, because I can choose wisely or I can choose poorly. So the best thing to do, and this is not a strictly correct statement, because the strictly correct statement depends on the algorithm that I'm using, and I've only kind of sketched an algorithm. But it always is closely related to, and you could say, I think, to leading order, always this function. So how should I weight my particles? Well, I should weight them based on, so I'm looking at a particle currently at position xsi, so s is some time before t, when I'm doing this resampling step, this weighting and resampling step. I look at the current position. I'd like to know the probability that the event is going to occur at, in the future at time t. If I did, this would be the function, the score to use to decide how many copies I get. So points that have a high probability of the event happening in the future would get a higher weight and would be more likely to be duplicated. Points that are sort of hopeless, in the sense that if the state is here, it's just the event's really not going to happen compared to the other points, they would get removed. This would be the optimal thing to do. Of course, the whole goal was to compute the probability of xt in A, so I certainly don't have this one. Okay, if I did, I wouldn't need to do anything. I'd be done. Okay, so what do we do in practice? Well, I'm going to describe things in terms of something I call a reaction coordinate. That name is borrowed from the chemistry literature on rare event simulation. You could also call it an order parameter. Really, I'm hoping that somehow this encodes progress towards the rare event. What could that mean? That could mean different things, but the way I like to think about it is that at least you might hope that it gets the ordering right. So if for one value of, I'm looking at the same time, this s is the resampling time, and I'm comparing 2 states, let's say, of the weather. And I could hope that if the reaction coordinate value at x is bigger than the reaction coordinate value at y, then the probability of the event happening in the future starting from x is bigger than the probability of the event happening in the future starting from y. So that somehow it gets the ordering right. That's never going to be achieved in practice, but it's maybe the most one could reasonably hope to have approximately. And I want to emphasize that this is really the key design choice. So out of this choice, once I've chosen theta, I'm going to build my score function, which I can think of as a rough approximation to this value, since I know this value is the optimal choice, by doing something really simple, like taking an exponential of theta, a scaled exponential of theta or something, right? To get something that's turn my reaction coordinate into a number that's non-negative and prefers states with higher probability over states with lower probability, right? Because I don't really know what else to do. Okay, so in practice, these schemes, if you're familiar with importance sampling, this is a sort of kind of importance sampling, and you may know that importance sampling is really, really sensitive to the choice of the reference distribution. This choice of score function, the scheme is very sensitive to the choice of score function as well. The scheme that I've described. So if you choose really well, you can do fantastically, just like importance sampling. And if you choose badly, you can be way worse than the naive estimator, just like importance. Okay, so in Rob's project, this first hurricane project, his goal was to, staying within this general DMC framework, make the algorithm more robust to the choice of reaction coordinate. And I've kind of led you towards what he ended up doing by making this statement about, maybe we could get the ordering sort of right in the reaction coordinate. So his idea, which turns into quantile DMC instead of just regular DMC, is to really given a reaction coordinate, build a new reaction coordinate that only depends on the order of the old reaction coordinate. So one way to do that is to think about dividing theta, the values of theta over the ensemble into quantiles, and then just deciding how much each sample should be biased based on which quantile it's in. Here's a little bit slicker way to do it. You just apply an inverse Gaussian CDF transformation to the empirical distribution. This is, if you look at this, this is the weighted empirical distribution for the original ensemble. I apply to that an inverse Gaussian CDF, okay, which is going to take me to a set of samples that are roughly Gaussian, because that's what the CDF transformation does. Okay, so now I have this reaction coordinate that I expect to kind of always be Gaussian, and I know how to bias a Gaussian in whatever way I want. I know that if I just do this kind of exponential twist of a Gaussian random variable, meaning scale the weights by e to the theta times the variable, to a constant times the variable, I know exactly what happens. I just shift the mean in that Gaussian. Okay? So again, a high-level version of this would be instead of looking at the values of the reaction coordinate, you just look at the quantiles, and then you prefer the high quantile, the samples in the highest quantile, prefer duplicating them over samples in the lowest quantile. The details of how one might do that are here, but if you don't, if you're not used to this kind of transformation idea, then it may not come through in the 2 seconds I'm giving it. So hopefully just focus on the high-level idea. Okay. Another way to think about this is, look, if the original process was an OU process, we could say exactly what the optimal way to bias the process would be, right? Because we can say everything about an OU process, a Gaussian process. And so this is like a kind of transformation that I can always apply that brings me back at least marginally, at least this variable is marginally normal 0, 1, and I can do what I would have done for an OU process to that thing. Okay? Of course, it's not an OU process, but that's kind of the idea under the hood. Okay, so what are the advantages of this? Well, it only depends on the order, which means, for example, any monotone transformation of theta, this scheme doesn't care about. Okay, you can apply any monotone transformation to the reaction coordinate, and it doesn't care. It ends up making it much more robust. So we definitely couldn't have done the problems we did with just regular DMC, where we build a score function kind of explicitly. We need this kind of adaptive feature. Okay, so now I'm going to go through some examples, and the examples are they are meant to kind of make points about what are the tricky parts in actually doing an application of this stuff, and how we dealt with those things. Okay, so these are not going to be super technical either on the science side or the math side. Okay, so this first example was rapid tropical cyclone intensification. So meaning we're interested in the rare event that a storm very quickly intensifies. What does that mean? You can think of that as meaning that the wind speeds increase very quickly, or you can think of it as meaning that the minimum pressure decreases very quickly. Okay, so we looked at two historical storms, Hurricane Earl and Hurricane Joaquin. we had actually already within the Weare software suite, there are initial conditions that correspond to each of these storms before they were big storms. So just when they're small tropical depressions, okay? So days, maybe 20, 30 days before they actually hit peak intensity. So we borrowed that state, those initial states, from the Weare software package. Weare is the model we're using for the simulations. Okay, it's a real model. You need, it turns out, to really resolve intense hurricanes, you need about a 1 to 2 kilometer resolution, and that's because you need to resolve the eye wall. So we're using an interdomain, a fairly small interdomain for that reason, 2 interdomain resolution. So the way that Weare works is you can actually track the center of the storm, and you can have nested domains. So in the center domain, you have the highest resolution, then you have a lower resolution, and you have a lowest resolution. So our finest resolution in the center is 2 kilometers. But we're starting from, again, many days before the storm when it's just a depression. It's not a hurricane, it's not a tropical cyclone yet. What we want to do, if we evolve forward from there, the original model, it will form a hurricane. Okay, there's enough information in that original state that it's going to form a hurricane that looks sort of like Hurricane Earl, the real Hurricane Earl that happened. What we want to do is force it to be more intense. Okay, so we're still looking at it. It was already going to be a hurricane. We just want it to be a more intense hurricane. We want to use our scheme to make it a more intense hurricane. Okay? So we need to choose a reaction coordinate. What we chose is so I told you could look at the minimum pressure, the minimum of the pressure field, so that's going to happen at the center of the storm. You could look at that as a measure of the intensity of the storm. So we use that as our reaction coordinate. If at the current time when I'm resampling, storm 1 has a lower core pressure than storm 2, then we're going to preferentially duplicate storm 1 over storm 2 because it's more intense. So that's kind of an obvious and not very clever choice. And we're going to see that costs us. Okay? Because remember, I told you that the best reaction coordinate, or the best score function, would actually be the probability of the event of the maximum intensity in the future. And I'm looking at a measure of the intensity right now, okay, as a proxy for that future intensity. That's not a very good choice, but hard problem, live and learn. Okay, so we do that for these 2 storms. We're using 100 simulations, 100 ensemble members for each of the storms. This model is stochastically forced. It's going to be different than the other model, but it's again all done within Weare. Okay, so Weare is in this case Weare is really just a button we can push. We wrap it with a Python wrapper that does all the splitting and relating and stuff. So so this is direct sampling. I told you that if I start from these initial conditions that we pulled from that are actually available within the Weare software suite for each of these storms, you will form hurricanes, tropical cyclones. Okay, you can see that the bulk of those dip into the Category 4 territory at some point at their maximum intensity. Okay, and then measure intensity by pressure. And the same thing for Hurricane Joaquin, which was a more intense storm. I don't have it labeled in here, and I don't even have it plotted in here, but the real storm is somewhere, meaning reanalysis after the fact, given the data going through. There's no, right, the only data we're using here is for the initial condition. There's no data being used later in the simulation. Of course, they did analyze what did the storm actually do, and so I could plot that's called reanalysis. I could plot that reanalysis trajectory, and it would be somewhere inside of this pool. Okay, but our goal, you see that we don't get any samples, in this case, in Earl's case, any samples into Category 5, and in Joaquin's case, we get 1 or 2 into Category 5. Our goal was just to see, because we're interested in the algorithms really at this point, just to see how far can we push the storm using this splitting stuff. And you can see on the right that We do manage to, so in both cases, we manage to get a lot more resolution, or significantly more resolution in the 95 to 99 quantile of the storm. If you were specifically interested in Category 5 storms for Hurricane Earl, well, we weren't super successful. Okay, we're more successful for Hurricane Joaquin, which was already a more intense storm. But probably the focus is just how much resolution do I get in what would have been, if I had more samples, the 95 to 99 percentile in this distribution. Okay, so we are successful there. That's just by the eyeball metric. I'll say more about speedups measured in a better way than just looking at pictures in a second. Just to tell you, there is a statistical cost to every resampling step. So in general, you want to resample as little as you can to get the statistics that you want. In this case, we in both of these storms we resampled 4 times. Okay, so that's not a lot. You can actually, if you look at these pictures on the right, you can actually see some of these trajectories ending, and that corresponds to resampling times. Those were trajectories that didn't survive to the next. Okay, so what were the positive outcomes? Well, like I said, so WRF is a horribly complicated thing that's been developed for a long time. You're not going to reach into it and make significant changes. So you really need a scheme that doesn't need to. That just can build a wrapper that calls WRF, runs WRF, stops WRF, gathers statistics, does the resampling, reinitializes WRF, and sets it going again. They're in fact, because, and this happens in a lot of fields, because things like WRF weren't written anticipating algorithms like this, there's more cost than there needs to be to that stopping and restarting. But certainly it's more realistic than reaching into WRF and adding some kind of a forcing, for example. On my own, that would be not realistic. Okay, we use this dumb reaction coordinate, the current minimum pressure, and we still manage to get speedups at best of about a factor of 10. I'll talk about how I measure speedup in a second. You can't measure speedup without some understanding of the uncertainty in your estimate.
I guess also, maybe go to work, but what is the, like you say, you want to preserve certain statistics or so? Yeah. Right, but I mean, you've said like you can create like
yes, so the estimate,
but what is the flip side where you're trying to preserve something about the true statistics of the problem?
Right, that's so that's the fact that this is the true statistics of the problem, right? There's no biasing here.
Oh, I see. Yes.
This involves a bias process, right? All of these xi's are not just direct simulations.
So that comes through the weights. Okay, yeah.
But we've designed the weights so that in fact this random variable expectation is still this number.
Okay, and that's why sort of this aspect doesn't appear anywhere, because you always design in such a way that it's unbiased, and so we don't worry about that.
Yeah. Yeah. The way to think about it is that many more of these XTIs are landing in A. I'm oversampling the rare event region.
Yeah.
But these weights are going to be smaller than 1/n for those samples that land there.
I see, but then you also need to basically make sure that also the variance of this estimator.
So then the whole it's easy to make sure that the bias is it's unbiased. Okay. The whole game is making sure that the variance is lower, and that has to do with your choice of reaction coordinate. And if you choose poorly, you could.
Okay, so I see. So far, basically, you use as a proxy how many of storms that fall into this, because you get basically more things to average over. Use that as a proxy for also the variance of this estimate that you measure.
So I haven't talked about how I measure the variance. It's tricky to measure the variance. I'm going to give you speedup numbers, which really require that I've measured the variance, right? I can't just say, so for the direct sampling scheme, I know how to compute the variance, right? It's just a binomial random variable. This estimator is just a binomial, for the direct scheme where these are all 1/n and these samples don't communicate, it's just a binomial random variable. So I know what the error bars are if you tell me the probability. But for the other scheme, it's more complicated. Now, speedup needs to be measured by saying, look, to get to the error bars of this scheme, how much work would I have to do in this scheme, right? If I just give you numbers, 2 estimates, you have no idea what the speedup is, okay? And that's actually a bit of an issue. I mean, the reason I'm dwelling on it a little bit is that it's an issue in rare event simulation, is that people don't measure the speedup in the right way.
Sorry, can I ask my question as well? I'm just interested, is it like exactly unbiased?
It's exactly unbiased, yeah.
And I guess the variance depends on like the data you choose.
So the variance really depends on, so there's the true variance and then there's your estimate of the variance. Your estimate of the variance very much depends on the samples that you generate. Like, so I'm estimating.
I mean the true variance.
Let's say I want to estimate the number 1 with a random variable whose mean is 1, but is non-negative and has enormous variance. What does that mean? That means that most of the time I generate a sample of that random variable, it has to be way below 1. Right? That's the only way its mean can be 1 and have a high variance. Is if most of the, so one thing that happens in rare event simulation a lot is that it'll look like you have low variance because you've generated a bunch of samples and they're all less than 1, and you don't know that the answer is 1. And you think, okay, well the answer is 1/10, and the variance is really small. Even though it's an unbiased scheme, that can happen. Because you haven't seen that one sample that comes along and gives you, instead of 0.1, 100 or 1,000. The one that corrects the bias, corrects the mean to 1. So it's very easy with rare event simulation to think you're doing well when in fact you're not.
It's hard to estimate.
You don't know that, yeah, it's very hard to estimate the variance. I'll talk about that in a second. First, I'm just going to say that, okay, of course, for the direct scheme, we do know how to estimate the variance, and for the other scheme, given an estimate of the variance, we can say what the speed up is. Again, it's the cost to get the same error bar, the ratio of the cost to get the same error bars in the two schemes. Okay. And so if we measure it that way, we see a speed up of about a factor of 10 in the best case scenarios, although I am using a conservative estimate of the error bars for the resampling scheme, which means they tend to be larger than the true error bars. Okay, and then in the worst case scenario, it's a factor of 2. So we're still doing better, but a factor of 2 you could decide is not worth all the trouble. Okay, the bad news. Well, we use this dumb reaction coordinate, which favors whoever has the minimum pressure, whoever's most intense at the moment. So what if in reality, the most intense versions of the storm actually intensify late? So compared to other storms in the beginning, the intensity's not so impressive. You do some resampling that removes that less impressive early intensity. But then if you hadn't, it would have intensified more later. And we actually do that. We killed some storms that would have actually formed more intense storms in Hurricane Joaquin's case. So that hurt us, increases the variance. Let's see. Right. So in that case, if you measure just the probability to reach Hurricane 5 status, we actually end up with a higher variance than direct numerical simulation. So this is an example where we actually made the problem worse. Well, the main thing I think I've suggested is that we should be. What time it is? Okay, that's fine. The main thing I think I've hopefully conveyed is that one has to be really careful when choosing the reaction coordinate. In this context, there's some nice possibilities. For example, there are models, including by people here at MIT, for the intensity, that model just the intensity of the storm. Okay, so given like the background wind field, just modeling the evolution of the intensity of the storm, which are very cheap compared to running WARF. So I could say, here's my current position. Here's my current, my particles are all here's the states of all my particles. For each one, I'm going to run one of these cheaper intensity models forward to the time that I actually care about and get a guess of what the intensity will be, the maximum intensity will be. That may not be perfect, but it just has to be better than what's the intensity right now. Okay? So that's an idea. I mean, maybe you could even, maybe there'd be enough order information even just in lower resolution WRF simulations for time. So I'm still getting the statistics from the high resolution WRF simulation. I'm just getting a sense about which way to sample from low resolution simulations. So there's things you can do. We haven't really had time to do it. And then application-wise, you could couple with models of other phenomenon to do, well, not for storm tracks, but for like flooding or storm surge. We could pretty immediately look at storm tracks. So, a storm, there are historical storms that, for example, just bypass big cities. You could ask what's the probability that they actually run into the big city, or what has to happen for them to run into the big city, or what will happen to the levees if a storm runs into a big city. So that's all kind of on the to-do list. Okay, so now let me pause for a moment and just talk about the variance estimation I've already mentioned. While they are unbiased, the samples that you generate are correlated. So if this was just an importance sampling estimator, you just had independent weighted samples, this is the variance estimator you would use. Okay, you can work that out. It's just this is just the fact that variance is the second moment minus the first moment squared. Okay, and the second moment for the weighted estimator would be. Okay, but if they're correlated, that underestimates the error. So you can go to the other extreme, which is when I said the conservative estimate, which involves taking each of my samples at the time that I'm, at the final time, tracing back their ancestry, back in time, and basically asking, okay, at the beginning, how many groups of trajectories are there that never interacted? How many independent groups of trajectories do I have? So that's pretty extreme because, in fact, over time, the process mixes a little bit, but it does give you an estimator that is provably, at least in the large sample limit, provably an overestimate for the scheme. Okay, so there's a lot of room in between these two, and I think a lot of room mathematically to work on better variance estimators for splitting schemes. Okay, but when I plot, in the next thing I'm going to go through very quickly, I'm going to be plotting pessimistic estimates of error bars and optimistic estimates of error bars. And this is what I mean. The one where I just assume that they're independent, and the one where I take the most pessimistic view of their dependence. And it's very strong. Okay, so, well, are there any more questions about the hurricane stuff before I go to another application? Okay, so moving up in scale, we're going to leave the Earth and move into the solar system. And so here you see Mercury and Venus, and what I'm interested in is the stability. So, they do roughly the same thing every year. That's why we're still here. But that's not going to happen forever. Okay, eventually, well, in 5 billion years, the sun, as you know, in 5 billion years, the sun is just going to envelop all this stuff. Okay, but before then, there's a chance that that Mercury, so Mercury's eccentricity is slowly changing over time, and there's a chance that it will either run into Venus, run into the sun, or get shot off into space. Okay, and people interested in planetary dynamics are interested in that question, both because it's interesting about our own solar system, but because maybe it tells us about to form life, you need a very stable solar system. So maybe it tells us about other solar systems, potential solar systems, potential life-supporting solar systems. Okay, so that's the reason that many people have studied this. So there's a very fairly famous paper by this person, Lascar and Gastineau, where they did, so these are just n-body simulations of, you take all the planets, we roughly know their dynamics. They include things like general relativity. You get the best model you can, and you run many simulations, in this case for 5 billion years. And you just look, this is a plot of Mercury's eccentricity over time. they're all started from, so the model here is not stochastic, it's deterministic, which means if I really start from the same position, if I start each copy of the solar system from exactly the same configuration, they'll stay the same forever. But it's also very chaotic over this time scale. So if I start from slightly different initial conditions, even very slightly different initial conditions, even initial conditions that differ on the scale of round-off error in your numerical integrator, they will deviate over 5 billion years. Okay, so and what you see is eccentricity is a very good signal for instability. So what you see is over time, the eccentricity going up, and here this indicates that one of those three things happened to Mercury. And you can see that it's more likely that it happens later. That's not so surprising. In the end, they get about a 10%. What do I have that as? Oh, this is 2 gigayears. Yeah. So about a 10% probability. About 10% of their runs go unstable. Okay, this was repeated with a different model later on by Zeeby, and he also got he got 6%. He has a little bit of a smaller ensemble, but for estimating a probability of about 6%, those have overlap in their error bars. And then we did it, and we get 12%. We did it with 1,000 samples, same calculation, maybe slightly different model, and we get 12% direct simulations. What we were interested in is actually what happens in this project, because you can do this by direct simulation, although it's very expensive. The 5 billion year calculation, because 10% is not zero. It's enough, a high enough probability. But we're interested in the 2 gigayear time frame, 2 to 3 gigayear time frame. Okay, there is a scientific reason for that I don't know a lot about, but I guess it's runaway greenhouse gases on Earth or something. Basically, Earth becomes uninhabitable anyways. Okay, so that's the problem we want to look at. We want to try and bias the simulation so we see more rare events, compute the probability accurately of a rare event in 2 to 3 billion year time scale.
Sorry, I missed this. Where's the randomness coming from for the simulations? Like
right.
The initial state?
The initial state. So in our case, we add a 1 centimeter perturbation to Mercury. Okay? 1 centimeter in space is not a lot. It's smaller than all of the other errors that you could imagine go into a simulation like this, from having a time step in your integrator, from not having maybe even asteroids passing by.
What's the results without when you choose it's a 1 centimeter, when you add a meter or millimeter?
It doesn't have a huge effect. I mean, I think they chose a bigger perturbation than we did, and they get similar numbers. So it doesn't have, at that scale, eventually it will have a big effect. And of course, if you ask for a rare enough event, like if I ask what's the probability of of this happening in, let's say, 100 million years, that would be completely dependent on the noisy perturbation. So there's you should think of this as, in the bulk, these kind of choices don't have a large effect on the probabilities. Okay, what do I mean? But if I go far enough into the tail, of course they are completely responsible for that. We're interested in tail probabilities, but we're interested in the physical tail. So it's not so far into the tail that all of these choices have a big effect. Okay, so this is the result, and then I'll talk more about it very quickly. But you can see that, again, from the eyeball metric, at least we're successful in generating a whole lot of these instability events early on. Again, using QDMC. Haven't told you about the reaction coordinate or anything else, but you can see that we are at least generating instability events. That doesn't mean that we're successful. We need to look at the error bars on our estimates. But you can see the resampling times here as well, so I won't say more about that. Okay, so then the big question is, how do we choose a reaction coordinate? Well, I've been showing plots of eccentricity, so the natural thing to do, which would sort of correspond to what we did with the hurricane, is say, well, let's favor samples that have high eccentricity. But then if you look at this data set of direct simulation at 5 billion years, and here I'm just zooming in, you can see that actually in eccentricity, these instability events, they happen at the last minute. First of all, it takes 100 million years just for two solar systems who are a centimeter apart to deviate, okay? To move appreciably away from each other in eccentricity. So this is happening within 100 million years. Meaning there's basically no signal. Eccentricity really isn't telling us that this is going to happen. It's just telling us that it has happened, okay? Here's one where you can see the eccentricity building. But most of these, the eccentricity just shoots up at the last minute. So we did it, actually, and that's how we kind of decided there was a problem. But if you use eccentricity as a reaction coordinate, you're going to generate too many of these kind of samples. It's still an unbiased estimator, but you're going to see in practice that most of the time you've way underestimated the probability. Okay? And then, you know, if you do this long enough, eventually you'll get that sample that actually happens this way anyways, even though you're biasing it the other way. And then you'll get, then you pop to a big overestimate. Okay. So eccentricity is very, very correlated with instability. It's very good as to say that yes, it's gone unstable or not, but it doesn't tell you anything about whether you're going to go unstable in the future, which is what we need for this algorithm. So, okay, long story, very, very short. We looked at something called the minimal orbital intersection distance, which is pretty much what it sounds like. You draw the orbit of two bodies, and you just ask what's the closest point on those two sets. That's actually very much like eccentricity. It's a close proxy for eccentricity, except that it goes down when you get you get an instability rather than up. So it's also not a good choice of reaction coordinate. It has very little predictive ability. But then we looked at data. We organized all of our instability events in the direct simulation, and we looked 400 to 800 million years in advance of the instability event. That's the only data we're looking at. And we did a regression on a bunch of variables that we threw into the pot. This is actually lasso. So we did a sparse regression on a bunch of variables that we threw into the pot on estimating the probability of instability when the only data that I get to see is 400 to 800 million years in advance of the rare event that I'm interested in. So, and it turned out that actually the wiggles in Moy, if you look at trajectories of Moy, when one of these events happens, it's going to go down, just like the eccentricity goes up. But if you look at the wiggles before that, 400 to 800 million years in advance, you'll see that the trajectories that went unstable, their moid was vibrating, even though the value the moid was taking was perfectly normal. It was vibrating within a normal range, but it was vibrating, whereas the others had a much smaller range. Okay? So we spotted that in the data, we included it in our lasso calculation, and it turned out that it was a good predictor. So that's the object we use for our reaction coordinate. And you know, the long story is we do quite well, getting speedups of about 100. You can see there's two, so this black one is direct numerical simulation. If I drew this plot longer, you'd see that our estimates do overlap well with the direct numerical simulation in the region where it's more reliable, where direct numerical simulation is more reliable. This is the region where you don't get any samples from direct numerical simulation. You can see that, okay, and I'm showing multiple plots here. That's because we actually did this QDMC thing looking at different time horizons. So one time horizon was 2.4 million gigayears, one was 2.8 gigayears, and one was 3.2 gigayears. All separate simulations, separate QDMC simulations with separate resampling times, because we were targeting different final times. You can see the overlap is pretty good. You can see that we're plotting two error bars, a thin one and a thick one. That's my pessimistic and my optimistic error bars. Okay, in computing speedups using those, we're getting factors of up to about 100. You get, not surprisingly, the greater speedups when you go to the less likely events. Okay, so rush through that, but that's everything.